Welcome back. In this video I'll be sharing a couple parts that I recently milled on the Shapeoko HDM. They're both equally complex in their own right. We'll talk about some of the operations, the feeds and speeds, and the tools that I use to calculate them. That would be HSMAdvisor and Millalyzer. And then we'll also talk about synchronizing your Fusion 360 tool libraries over to both of those platforms using a tool I wrote. Stick around. Alright, so first we're going to talk about a couple parts that were milled on the Shapeoko HDM and the details around what they are and what went into creating them. This first project was an Insta360. I'm not sure if you're familiar with that. It's a 360 camera and an industrialized hardened enclosure that's waterproof that would allow that camera to still get a full 360 field of view and create this modular core unit that can be used as this minimal version as well as retrofitted into this maximum version for industrial strength and to protect it from the elements, those being carnivorous animals. That said, there was a lot of details and tricks to getting these faces milled out with all their profiles, and although it doesn't look like a very complex part, there are no really good parallels to mill this on, so I basically did flip jig on both of these. And we'll walk through those steps, the feeds and speeds, and the operations that went into that. And for that, let's jump over into Fusion 360. All right, over in Fusion 360, I have a base model for a Insta360, which is a 360 camera. If you're not familiar with that, I'll put a link in the description. But it basically records 360 environments, and it's a handheld camera that you can put in a lot of applications. It's not very industrial, though. It is waterproof, but it's not very rugged in terms of being to withstand, the bite force of carnivorous animals and things like that. So this particular project is around that. It's around protecting the device and creating an industrial sort of hardened enclosure that will prevent it from being crushed under those circumstances. And for this, we start out with the camera. There's a couple of variations here. So this is designed to have a modular core. And so the first thing we did was extend the battery life by creating this insert. This insert would be responsible for having battery holders. And those extra batteries would provide additional power to the device, extending its battery life to almost 4 or 5 hours in length. Now with that, we needed to protect that. So there's a couple different variations. There's a minimum frame, which is this smaller guy. And then the one that you'll see today is the maximum frame, which is a large enclosure. This is allowed to be mounted onto a pole or some other apparatus that will hold it in place. Now the internal battery compartment is resin printed, and then there's a potting compound that protects all the electronics from humidity and moisture and stuff like that. But then there's a couple plates that go on the front and back side of this that you can see. That would be the front face and the rear face. If you look at those have nice 8 countersunk screws that hold it in place. It's got a little hole for the microphone. And if we isolate this, then you'll get a better idea of the details and complexity that went into this. The reason why this is kind of tricky is that camera actually had to be countersunk into there. And you see that the form of that camera is indented in this 4mm plate. And in addition to that, using extruded seals, you can, or dispensed seal, whatever you want to refer to, a bead of silicone is placed in this groove that seals around the outer perimeter as well as around the lens and microphone to prevent too much water ingress. Like splashing and direct hose spraying on it, it'll be fine. Submergence, maybe not, needs to be tested. But that said, this was one of the first parts that we'll walk through the operations in milling. And it's really just got this countersunk area, which is really smooth to align and position the camera perfectly up against that. And the reason why it needed to be countersunk, because this is only about 1mm thick. And the reason for that is obvious to ensure that the lens gets full display and visibility to capture that 360 video. If you obscure or you clip that lens in any way, then you're going to get some problems with the way that the video is stitched, and you'll see this enclosure. By bringing it this close to the face, this becomes entirely transparent. You'll see in some of the sample video that this has got a 360-degree view, and it's like this enclosure is not even there. So that said, let's look at a couple of these parts. We'll walk through the operations. Specifically, we'll start with the faces. So let's get rid of this frame max. We'll walk into the manufacturer tab and look at the operations that went into this. All right, initially we used an indexable facing mill. It has 3 indexed cutters in it. This is a 1-inch diameter, and milled this down to size. You can see that this is located at the bottom of the stock, so we had to face off this top material. So doing that would just be this facing operation. Let's see, the feeds and speeds for that were only at 1200 RPM with a 25 inches per minute to give it a really clean, nice finish. I was doing step downs of 15 thousandths just to go light and easy on this. Even though we could have pushed a little harder, I wanted to make sure that it had a nice clean surface to work with. After that, using the aluminum shredder, we hit it and kicked it up a notch to be a little bit more aggressive to dig out this area. 1800 RPMs, 100 inches per minute using aluminum shredder bit, and this would be at 120 thousandths step down. So we took out this center area pretty evenly. As this was a 3D adaptive operation, it would work its way up into these finer details, leaving 20 thousandths to come back and finish it with. After it was roughed out, I came back with a morphed spiral, and that would take all of this finishing detail to the next level, which would finish it off and make it just buttery smooth using a 1/4-inch ball end mill, and we were running that relatively light, well, 20,000 at 60 inches per minute. Could have gone a lot heavier, but I wanted to have a really nice finish on that. The particular bit I used was a 3-flute ball end mill. Once that was completed, using a 1/16 inch ball end mill, 17,000 at only 8 inches per minute, that would be the trace operation that would be performed to create these dispensed gasket recessed areas. And so that was just ran slowly to give it a nice clean edge and finish on that channel. Next was a simple drilling operation with a 3mm drill that would drill out the 8 corresponding holes in the plate. And finally, we used 2D contour operations using a 1/8 inch flat end mill to cut out the aperture as well as the perimeter of the face. We had several tabs spaced around 3 inches apart, and the feeds and speeds on those were very conservative. Although it was 20,000 RPMs at 55 inches per minute, the depth of cut was very shallow at only 10 thousandths of an inch. Wanted to be careful with that, cut that perimeter as it's a slotting operation. There was about an eighth of an inch that needed to be faced off the top, the face, and the rear of the part. And for that, I started with the aluminum shredder to do an adaptive clearing to clear away a majority of that stock. Let's see if we can get both of those in view there. And this adaptive operation will step up and get that nice angle. It's going to leave a rough finish, obviously. The aluminum shredder was run at 19,200 at 101 inches per minute, and with a optimum load of 75 thousandths and a roughing step down of 280 thousandths. There would be a 20 thou stock to leave that would give us some room to play when we came back and finished these angles. Next step was to bore out these two mount holes, and those would just be bored out with a 1/4 inch 3-flute flat end mill. Nothing tricky there. 18,000 RPM at 60 inches per minute, and I believe what I do, a 7 thousandths pitch, so a very non-aggressive boring operation to ensure that the sidewalls and the finish was really good on that. Next, I used the same 3-flute flat end mill to finish up these flat areas and bring those down to spec. Nothing really complicated with or aggressive with those. At 19,000 RPM, 100 inches per minute, just shaving off that 20 thousandths and leaving 2 thousandths on the radial to clean up on our finishing passes. We'll come back with a 3/8 end mill and really give it a nice sidewall. The next step was to do a spiral operation that would finish off this angle that we have here. It's about 15 degrees, and that was ran at 1700 using a 3-flute 1/4 inch ball end mill, 1700 RPMs, 125 inches per minute to shave off that 20 thou that was remaining on there. That left a really nice finish, and you can see it's just a really shallow step over to make sure that there's no tool marks or tooling operations that would leave blemishes. Finally, we came back with that same 3mm drill to drill out the 1/4 inch deep holes using a chip breaking operation. For that was at 15,000 RPMs, and the plunge was only around 10 inches a minute. Final operation was to clean up the sidewalls here. These would be cleaned up with a 3/8 inch 3-flute flat end mill. It gives it a really nice sidewall finish. 20,000 RPMs, 100 inches per minute, 1/2 inch step down. This part was then flipped over, and the exact same operations were ran on the second side. The frame that was around it would be used to hold it in place using the mod vices on my fixture table. With both parts complete, I took them over to my drill press where I ran a Scotch-Brite wheel on them to scuff up the surface, to rough it up. And for the facing up applications, I'd be powder coating those. And for the max ring, it was really just to remove any final tool marks and just prepare it for the finish that I put on it. Not sure what that's going to be yet. Might be a clear powder coat, something of that nature. The Scotch-Brite wheels don't last long, but they leave a great finish on your part if that's what you're going for. With the faces complete, they were powder coated, and it leaves with a matte black powder coat. This was cooked in just a small oven, which leaves a great finish on these, and they're pretty durable. Didn't need to coat the insides because that will be where the camera gets mounted and the seals are applied. In terms of the max base, that's going to be left in its current state, which was Scotch-Brited, has a nice finish, removed any unwanted tool marks, just to finish it up and clean it up. And that said, that's pretty much where I'm going to leave them right now. These are prototypes. We're working through the design, and this is the first iteration of that. Just wanted to share some of those parts and operations and tips and tricks that I use in milling these out. That said, these operations took some time to set up in Fusion, as you can imagine, and running those numbers and getting the feeds and speeds just right was something that took a little trial and error. For that, I used HSMAdvisor and Millalyzer. Now, you may know that, obviously all the tools are set up in Fusion 360, and all of my tools are divided into vendor categories: Carbide3D, Amana, EVA1, Kodiak, cutting tools, helical, Harvey tool, Lakeshore. Right, so I have all of my individual catalogs in those respective locations. But to get them over into HSMAdvisor, I needed to export those libraries. And you may have seen my previous video on the software application that I wrote to translate these libraries to a compatible HSMAdvisor. It saves me a lot of time to load those up and use them in the HSMAdvisor. So in HSMAdvisor, I primarily use it to get ballpark figures for my feeds and speeds, and for that I will they have a tool database over here as well, and here's where I import all of my libraries from Fusion 360 using the software that I created to convert them. So once they're over in this environment, I can select the exact tool that I'm using in Fusion 360, and then I can tweak around the depth of cut and width of cut and adjust the aggressive aspects of the feeds and speeds. And ultimately, once I have my initial RPM, feed rate, and chip load, then I will take that back over into Millalyzer and tune it for performance and for manufacturability. One thing to note also in HSMAdvisor is the ability to set up these machine profiles. I've already got them created for the machines that I use, and that identifies torque limitations and power and rigidity of the gantry and that sort of stuff. I've shared those up in their HSMAdvisor cloud if you need to download those. So like I said, once I have these base settings, I'll take them over into Millalyzer. In Millalyzer, that allows us also to go in here and pull up the same tool, use the same parameters, and calculate what the physics of stress and heat and strain on the tool looks like for one revolution of your end mill. The problem I always had was when you're using Millalyzer, it's also got its own tool library, and the only way to get your tools over in was to create a new one. You have to enter all the same parameters that you enter in Fusion 360 or HSMAdvisor. And it's such a time-consuming process to create the tools and the libraries in Millalyzer or HSMAdvisor that I extended my tool library converter to now take the Fusion 360 library and convert it into a Millalyzer compatible CSV file. So for that, we'll pull up my file real quick. So this is my little converter. Allows you to select the file which was exported from Fusion 360, and then you can either create a HSMAdvisor library or create a Millalyzer library. creating the Millalyzer library will import the Fusion 360 and convert it into a Millalyzer format and save it out as a CSV file. That saves tons of time. The only problem that I have now is that loading those libraries into Millalyzer, you can only load one at a time. So is that you can just load all of these CSVs into Excel and combine them all, and then you get one giant library that has all of your tools. Conversely, you could load the individual libraries that you need, whether it's a Mana or Helical or Datron or whatever library you may be using, and that's a lot easier than having to re-enter these tools manually. So that said, with these tools being able to be synced up to the Millalyzer and HSMAdvisor, it allows you to work through the aspects of improving your feeds and speeds and tuning them and really pushing the limits. The thing I really like about Millalyzer is your ability to plug in those values of what you think you want to run, whether it's dry, and then you can run these optimizations that will ultimately run variations of your axial and radial engagement and give you alternatives on how aggressive you may want to go. So this particular one happens to be sorted by material removal rate. You can see 472 inches a minute at the top. It's going to be too aggressive for me. With the HDM, 3 is kind of the ballpark for the 1.5 kilowatt spindle, and depending on how stable the fixture is or the finish or how much I want to let it just run on its own, that will determine on how aggressive I want to go with this. Often if you push the limits on this HDM, then I'm going to have to babysit it. I'm not going to feel comfortable. You might wear or break your bits sooner rather than later, but Millalyzer gives you all those options to tune and tweak this to get the most out of the machine. Whereas HSMAdvisor is going to give you a ballpark that based on your input on how aggressive you want to be with feed speeds and fixture, and this will actually tune it down to the specific harmonics and engagement physics algorithm that will give you much more reliable and accurate depiction of the performance. And you can visualize that. And so in this case, there's 3 flutes here, so you can see during one 360-degree rotation, these are the 3 flutes engaging in the material, and it'll give you the axial in plane. And ultimately, you want this to be as smooth as possible because the load on the tool edge and then the loss of load, that variation can cause it to be loud in the harmonics of the cut, and ultimately result in how quickly and efficiently you can remove material, as well as what the finish on the surface looks like when the cut is complete. So all of that considered, using those tools and synchronizing the libraries simplifies the process of having a tool chain that works systemically driven from the tool libraries that you create within Fusion 360. So hopefully you enjoyed this look at these 2 parts that were pretty unique in regards to milling operations performed on the Shapeoko HDM, as well as the software that I wrote that synchronizes your tool libraries to the Millalyzer as well as HSMAdvisor. If you're like me, you probably build out your tool libraries in Fusion 360 and then syncing them over to these other platforms so you can calculate your feeds and speeds and optimize it for manufacturing is a must-have. I'll make that download available. I'll put a link in the description below. If you want to support the channel, subscribe to the channel, ring that notification bell so that you get updates when new videos are released, as well as you can check out my Patreon or the website. Occasionally I sell some of the stuff that I make here. That said, be safe, have fun, and I'll see you next time.
Hey, if you liked the video, please subscribe to the channel. It's how we're building the community. Also allow me to bring better content. Also check me out on these other social networks. There's lots of cool stuff there too.